This is going to be the first of two lessons on exponential and log functions. I'm just going to split it up into two parts so it doesn't get too long. And I want to start by contrasting polynomial functions, of which quadratic functions are an example. One example. Polynomial functions involve powers of x. Okay, it's like a quadratic function might have x raised to the second power and x to the first power in it. You can have other polynomials that would be something like x to the fifth minus 4x cubed plus 8. Any expressions involving x raised to a constant power multiplied by a constant, and those things added up, those are polynomials, and they kind of follow a common logic. They are different from what we're going to talk about today, exponential functions, which involve x in the exponent. So a constant raised to the power x. So something like 5 to the x power, or we might say b for base to the x power. Okay, so exponential functions are used to model things where the rate of growth is proportionate to the actual size. So populations, large populations grow faster because you have more people available to be potential parents. They also are used to model the spread of disease. The more people who are infected, the more other people they can infect. Okay, so I'm going to do a very simple example of contagious disease. So what we're going to think about here in this example is that each person who has the disease is infectious for 1 week, and then they're not anymore. So simplifying like crazy. And during that week, they will infect 2 other people. And I'm going to assert and I'm going to show you that that is going to create what we'll call exponential growth. So let's think about now the number of cases, the number of new cases in each week. Okay. And y is a function of time. A lot of the time when we're working with exponential functions, the argument, the domain variable, the independent variable is naturally a time type of application. So we often use t rather than x. And I'll use that here. I think I'll actually be going back and forth between t and x because you will really see both of them. Okay, and so t is weeks. And so the idea here is that y, the number of new cases, depends on what week we're in. So let's just make a table with this simple example. And let's start off in week 0. We've got 1 person infected. Okay, so that person is contagious for a week. And by week 1, they've infected 2 people. The first person is no longer contagious, but now these 2 people each infect 2 more. Okay, so we get 2 times 2 equals 4 new cases in week 2. By week 3, the people who got sick in week 1 aren't contagious anymore, but all 4 people who got sick in week 2 are contagious, and they each infect 2 people. So you've got 2 times 4 here, got 8. And you're starting to see the pattern, I think. By week 4, everybody who got sick prior to week 3 is no longer contagious, but those 8 people who got sick in week 3 each infect 2 people. So you get 2 times 8 the number of new cases in week 4 is 16. So let's skip ahead. What do we think happens after, say, 12 weeks? That would be 3 months. Okay. The pattern that we're seeing here is that Y is this base number 2. It's pretty close to what epidemiologists call the R0, the number of other people that a single case will infect. It's that 2 raised to the power t. Okay, so here is our little exponential function. So by week 12, what we're saying is that that should be equal to 2 to the 12th power. That's 4,096. That's pretty big. What about after 20 weeks, 5 months? Doesn't seem like that long a time. 2 to the 20th power. Now we've got 1,048,576. Okay, and so this is the thing about exponential growth. Things get very big very fast. They start off, it's kind of, oh, no, 1, 2, 4, whatever. These are numbers we can wrap our brain around in a fairly short amount of time, 20 weeks. We're getting into really, really large numbers, and it's continuing to accelerate, right? Because you're getting more and more cases here. Okay, so in real world cases, if this was math camp for epidemiologists, we'd be right away going into more complicated models with taking account of the fact that behavior might change. So the rate at which people infect each other might go down, or the way that people are encountering each other might change. We might exhaust the population. In the real world, exponential growth can't go on forever. So real world models of disease or population or other things that have an exponential component have something in them that flattens them out eventually. Okay, that's so for reality, that's, rest assured, that's how real world processes go. But for our example, for just understanding these exponential functions, let's stick with this kind of simple function, okay? So sticking with that, copying it here. So if our number of new cases in any week is 2 raised to the power t, t being the number of weeks, something we might want to ask is when, at what value of t would we get to some kind of milestone? When do we get, say, 10,000 cases? Okay, well, we could tell from the table that we had before, if we were at 4,000 in 12 weeks and 1,000,000 in 20 weeks, it's somewhere between 12 and 20, but we might actually want to know what value of t solves 2 to the t equals 10,000, right? That's, right now the papers are full of speculation about when particular numbers of cases will hit particular benchmarks in different places. So this question is put in even a mathier form here. We might be saying, what power do we raise the number 2 to get 10,000? What power do we raise the number 2 to give an answer of 10,000? Okay, that question sets up the definition of a logarithm. You can almost think about this question is kind of implying the definition of a logarithm. Okay. And so the answer to that we would write as the base 2 log of 10,000. So look at that. Base 2 logarithm of 10,000. Okay. This definition is both important and useful, so I kind of want to belabor the definition of a logarithm and write it a few more different ways. Okay, so definition. In one sense, they're plural, but they really are all saying the same thing, just writing them slightly differently. Okay, so one would be if y equals b to the t power, then t equals the log b of y, the base b logarithm of y. Okay, so that's one definition. There's two others that I've actually kind of numbered in the notes. I'll use the same numbering here. Okay, another way to say this, D1, being here kind of as promised, I'm going to switch to x instead of t, that x equals b raised to the power log bx. Okay, let's get that for a minute. And here's another way to say the same thing. X equals base b log of b to the x power. And let me maybe put some parentheses here to make sure that everything's clear of what's being implied here. So in this first D1, we're saying that we're raising b to the power log bx. In D2, we're saying we're taking the base b log of b to the x. And what I want you to see in both cases is what we are doing is we are creating an inverse function. Okay, we're applying a function and its inverse. So these are inverse functions. If you raise a number to, actually let me start on the inside here. That's a better way to do it. Okay, if you take the log of a number, okay, so you take the log of a number and you get a different number, how do you get back to what you started? Oh, you take the base of the log and raise the log to that power. That's D1. Okay, so how do you undo the log function? With an exponential function. And when you do the log and then you undo it with the exponential, you get back to the x that you started with. So in both of these cases, you're starting with x and getting back to x, and that's what inverse functions do. Here, if the first thing you do is raise b to the x power, how do you get back to x? You take the base b log. So we're going to use, like I said, we're going to use these definitions to solve problems, and these are particularly useful in some of the practice problems you have and some of the derivations that we'll do. That's why I'm giving them the little D1 and D2 labels here. So let's look at graphs here. So I've got a graph of an exponential function and a graph of a log function. So these are the base 2 exponential function and the base 2 log function. And I'm asserting that these are inverses of each other. One way to see that they're inverses is just to, if you can kind of mentally take the exponential function. I didn't want to do, I wanted to just highlight it. There. A lovely color, isn't that nice pink? Okay, you take this function and kind of, you think of just like rotating it. which is what you're doing. You're switching the vertical and horizontal axes, you get the log function. Okay, so here I'm using, in both cases, y for the vertical axis and x for the horizontal axis. So they really, we're not getting back to an x here, but the log function is the exponential function, just sort of rotated 90 degrees there. And I just want to sort of point out some things. First of all, both of these are, the pink's pretty, but it's a little bit out there. So let's go back to purple. They are monotonically increasing. Okay. Monotonic just means it's only increasing. Okay, it's never turning around. It's not like those parabolas that went up for a while and came down for a while. Both of them are only going one direction, and it's increasing. Okay. For the exponential function over here, so here's our exponential. The domain is all real numbers, but the range is positive numbers. And you see that in the graph. Any number you want, you can take that and put it in an exponent for a base. But when you have a positive base, you're never going to get a negative number by raising it to a power. The flip side is true for the log function, right? If you say something is the inverse, it means you're flipping the domain and the range. So here, the domain is just the set of positive numbers, positive reals. Where's the range? It's all real numbers, okay? You can't take the logarithm of a negative number. It really doesn't make sense. One thing that you don't see in the graphs, but I think if you think about for a minute, you'll probably realize, and if you don't realize it, take my word for it. It doesn't make sense to use any base that's not a positive number. Okay, so in all of these cases, the assumption is that the base is greater than 0. You really can't define functions that are coherent in any way with negative numbers as bases. And again, just sort of stepping out, connecting back with things that we said in prior lessons. In the context that we're working in here, y and x are the variables, the domain and the range variables. They're the relationship we're trying to understand. The base b could be 2, it could be another number here, is just a parameter. Last pair of comments on these graphs is, no matter what our base is for an exponential function, the functional value of 0 is 1 for any exponential function. And that is just a direct result from the rule of exponents that says for any positive number, you raise it to the power of 0, you get 1. So no matter what base we have, the exponential function is going to pass through this point x equals 0, y equals 1. And because they're inverses of each other, that means that for any log function, f of 1 will be 0 for any y equals 2. Okay, so more to say about both exponential and log functions, and I will see you in the second part in the next lesson.